Hey guys, this is Mr. Bennett, and we are looking at video 4-3. We're talking about something called valence electrons, continuing our discussion of electrons and why they're important. That's actually a question I want to revisit. We talked about it in our first video, and in our first video we said that the electrons are important because they determine how the atom will react chemically. So if we think back, we've already talked about the other subatomic particles. We know that protons determine the identity of the atom. They tell you what element it is. Neutrons control what isotope you're looking at, the overall mass of the atom. Electrons determine how it reacts chemically. Specifically, we want to talk about the outermost electrons, the electrons on the outside of the atom. If we think back to the Bohr model that we talked about, remember Bohr described the atoms as the electrons rather in the atoms as traveling within energy levels. So if you have the nucleus at the middle, you have the first energy level which holds 2 electrons, and then you got here and you have your second energy level with its electrons, okay, and then let's say that there's 3 electrons in this third energy level. Well, these 3 electrons in the third energy level are what we call the outermost electrons. They have a special name. They are the valence electrons. Valence electrons are electrons found in the element's highest energy level, meaning the outermost level. Why are they important? Because they're on the outside of the atom. When this atom comes in contact with another atom, these are the first electrons that will come in contact with that other atom. So they're going to react, they're going to be responsible for interacting with another atom. It turns out the periodic table is actually designed so that when you look at an element, you can tell what its valence energy level is. It turns out the way you tell that is by the row that it's in. So hydrogen and helium, they're in the first row, so therefore their valence electrons are in the first energy level. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon, they're all in the second row, so their valence electrons are in the second energy level. This guy here, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon, their valence electrons are in the third energy level. And potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromine, and krypton, their valence electrons are all in the fourth energy level. So when it comes down to it, you can tell their valence energy level, meaning their highest energy level that they use, just by what row they're on in the periodic table. Okay, so let's talk a little bit more about valence. First of all, if your valence orbitals are only partially filled, you're considered to be reactive or unstable. If an element has full valence orbitals, it's considered to be stable or unreactive. Okay, so 2 examples here. Hydrogen has 1 electron, so it's in the 1s orbital, and we would draw it just like this. I'd like you to draw this in your notes. Helium, on the other hand, has 2 electrons, so they're going to fill the 1s, and they end up looking like this. Helium's 1s is completely filled, so we would say that it is stable or unreactive. Hydrogen, on the other hand, is only partially filled, so we would say that it is reactive or unstable. Okay, so this comes down to the idea that hydrogen has 1 electron in its valence, or we'd say it has 1 valence electron. Oxygen, on the other hand, okay, another example here, this would be its electron configuration. It has 2 electrons in the 1s, 2 in the 2s, and 4 in the 2p. So how many valence electrons does it have? Well, we could count all these up, but they're not all valence electrons. The valence electrons are only found in its highest energy level, the highest energy level that it uses. Another way of thinking of it is, when we look at the periodic table, oxygen is in the second row. So all of its valence electrons are in that energy level. So its valence electrons are in the 2s and the 2p. So 2 plus 4 gives us a total of 6 valence electrons. Okay, so let's look at an example. Here we have silicon or krypton. Which one is more stable? Now I could write out their complete electron configurations, but we're really only caring about its final valence orbitals when we're talking about stability. So in this case, silicon, its last electrons fill the 3p sublevel. And p's, remember, have 3 orbitals. So that's 2 electrons. So if I fill this in following the 3 rules, meaning off-bow, Pauli exclusion, and Hund, okay, Pauli says that we fill them in parallel until we have to double up, then we would go opposite, right? And then Hund's rule says that we have to put 1 electron in each spot before we can double up. Krypton, on the other hand, its electrons are in the 4p. Okay, it's still a p, so it has 3 orbitals, just in the 4th energy level, and it contains 6 electrons. So I fill these in, Notice I'm doing parallels first to follow poly. I did Huns, so I put 1 electron in each spot. Now I'm coming back, following poly exclusion, which means I have opposite spin. And there's my 6 electrons. Krypton is completely filled, right? This is filled. P can only hold 6 electrons total. So this is filled, which means it is the stable one. Silicon, on the other hand, isn't full. It can hold another 4 electrons within its P sublevel, so we would consider silicon to be reactive or unstable. All right, let's talk a little bit more about what this valence means. Hydrogen, we already said that its electron configuration is 1s1. Okay, its valence electron is in the 1s. If we look at lithium, its valence electron is in the 2s. Okay, it's 2s1. Sodium, its valence is in the 3s1. And if we look at the periodic table, it turns out that these guys are directly lined up. Okay, they're in the same column. So here's hydrogen with 1s1. Here is lithium with 2s1. Here's sodium with 3s1. So if we want to see what other elements are similar in terms of electron configuration or in terms of their valence, potassium is going to be 4s1. It's in the 4th row, okay, and it turns out its valence is going to be, again, s1. Rubidium is going to be 5s1. Cesium is going to be 6s1. And francium is going to be 7s1. Turns out when they're all lined up like this, all the elements in the same column, okay, they will all have the same valence. It's just that energy level is going to go up because you're going down the periodic table. So when they are grouped up like that, when they are all lined up in the same column, we call this a periodic group or family. The columns are groups or families. And groups or families are all elements with similar chemical properties. Those elements I just showed you, potassium, sodium, cesium, rubidium, they're all highly reactive with water. Okay, they're explosively reactive with water. Okay, has to do with the fact that they all have that S1 valence. Okay, so they all have similar electron configurations. Okay, in the case of lithium, for instance, it's 2s1, and sodium is 3s1, etc. Okay, similar electron configurations means similar chemical properties. So if we were to look at the periodic table, we could fill it in based on the valence. So in other words, hydrogen would be 1s1. Helium, we add an electron, okay? In other words, we go from atomic number 1 to atomic number 2. Helium is 1s2. Now you have a blank periodic table. I want you to fill this in just like I'm filling it in. Okay, so if we add another electron to follow the increase in the atomic number, lithium would be 2s1. And then beryllium would be 2s2. Now, if we remember our sequence, after 2s, we go to 2p. So as we add another electron, we're going to go to, 2p1. We add another electron, this is 2p2. Nitrogen will be 2p3. Oxygen will be 2p4. Fluorine will be 2p5. And neon will be 2p6. Okay, so first row, we did the second row. Now we're going to do the third row. What I'd like you to do is see if you can fill in the third row based on what we know, okay, based on what we've done so far, on your own. So pause it and try. Okay, so if you pause it, again, third energy level rather, this would be 3s1, 3s2, then we go to 3p1, 3p2, 3p3, 3p4, 3p5, 3p6, okay? Then we go down here, this would be fourth energy level, so 4s1, 4s2. Now we do something tricky in here. If you remember back to our previous video, it goes 3s, 3p, 4s, and then 3d. Remember how the energy levels overlap? The 4s ends up having lower energy than the 3d? It makes sense. We just filled the 3p, then we filled the 4s before we fill the 3d. So this will be 3d1. That means we have one electron in the 3d. Then to get to titanium, we have to add another electron to the 3d, so it's 3d2. Then vanadium is 3d3. See if you can fill in the rest of this on your own, and then see if you get it right. So pause the video and fill it in. Okay, so this would be 3d4, 3d5, 3d6, 3d7, 3d8, 3d9, 3d10. Then this would be 4p1, 4p2, 4p3, 4p4, 4p5, and 4p6. That's as much as you need to know in terms of the valence. okay? But you understand how they get filled in. Now, we could do this. This is crazy, all right? It's a lot of details, but there's actually an easy way of doing this. And if you flip over your notes, you'll see you have another blank periodic table. Now we're going to map it out into just kind of some big sections or big chunks. It's a lot easier to deal with. So this section over here that contains all of the S, notice there's one piece of it hiding over here with helium, so it belongs over here as well. This is what we call the S block, because these elements all put their valence in the S sublevel. These guys down here, we call this the D block. Now there's a trick to the D block. The thing is, 3D is in the 4th energy level. So what I remember is the D in D block stands for down 1 level. In other words, the 3D is down 1 level from where you think it should be. In other words, it's not in the 3rd row, it's down 1 level, it's in the 4th row. Okay? This block over here, we call the P block, because these elements put their valence in the the P sublevel. And then finally, this guy's down here. Even though we don't use them for our purposes, we do need to know what this is called. This is called the F block. So they put their valence in the F sublevels. And I do want to point one more thing out. Notice the S block is 2 columns wide. That's because the S sublevels can only hold 2 electrons, right? The D block is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 columns wide, because D sublevels can hold 10 electrons. The P block is 1, 2, 3, 4, 5, 6 across. It can hold 6 electrons. The F is 14 columns across, which means the F can hold 14. So remember how we had to memorize, or you were thinking you had to memorize how many electrons each of the sublevels can hold? Turns out the way the periodic table is organized, you just have to, if you know the blocks, S block, D block, P block, and F block, look at how wide it is. That tells you how many electrons that particular sublevel can hold. Okay, so let's do a little bit of practice. What we're going to do here is we have the valence. I could write out the entire electron configuration, but I'm just looking at the valence sublevel, the last sublevel in the electron configuration. So we have an element here whose electron configuration ends with 4p4. Let's see if we can find it on the periodic table based on what we know. So the 4 tells us the energy level, which is just another way of telling us the row. So in other words, this is going to be in row 4. The P tells us the block. Okay, so we're in the P block, which means we're all the way over here in the P block. Okay, and we're somewhere again in the 4th row. The 4 here tells us the number of electrons. So in other words, we're in the P block and we're 4 electrons over. So 1, 2, 3, 4. So we're dealing with selenium. Second example, 5s2. What I'd like you to do is see if you can find this one on your own right now. So pause the video and try. Okay, so if you paused it and you tried, what you should have seen is 5 tells us the row or the energy level. So here, we're in the S block, which means we're right here, and we're 2 electrons over. So 1, 2. So we're dealing with strontium. Okay, one more example, 4d5. This is a tricky one, so be careful. Try this on your own and then see if you got it right. So pause the video. Okay, so if you paused it, first thing you should have noticed is 4th energy level, right? So theoretically, you're right here. But it's the D block, and D stands for down 1 level, which means that you're actually in the 5th row. Okay, then we know it's the D block, so it's in the middle. Okay, and it's 5 electrons over. So 5th row, D block, 1, 2, 3, 4, 5. So we're dealing with TC or technetium. Okay, all right. Now I showed you this element in a previous video. So, and what I said was there were 2 ways to solve it. So the first easy way to solve it is you count up the electrons. So 2 plus 2 plus 2, which tells us 6 electrons. If we balance that out with protons for a neutral atom, we know the atomic number is 6. That tells us it's carbon. Okay, but let's say we got crazy, and let's say that instead of 6 electrons, let's say that our element has 27 electrons. So in other words, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then let's see, that would be 10, 18, 20. So then it is 3d7. Okay, so that's its full electron configuration. If I had to add this all up, it'd take me a little bit to say, okay, 27 electrons. Instead, very quickly, what I can do is recognize that its valence is 3d7. Okay, so that tells me third row, but it's the d sublevel, so I go down 1, right? D is for down 1. Find the d block, right? And count over 7. 1, 2, 3, 4, 5, 6, 7. That tells me that I'm dealing with cobalt. So that was faster, just looking at 3d7 and locating it here was faster than saying, okay, let me add up all these electrons, especially if I do my math wrong and I accidentally add it up and I get to 26 or 28 or some other number. Okay, so the best way to do it is to find its location on the periodic table if you know where the blocks are. Okay, so let's do a little bit of practice and then we're done. First practice question. We'll do this together, and then the other ones you can try on your own. So it says, which element has the same S and P valence electrons as chlorine, but is in the 4th energy level? So same S and P as chlorine, but in the 4th energy level. I'm gonna jump back here. Chlorine is right here. It is in the 3rd energy level. We want something that's in the 4th energy level. So in other words, we're gonna drop down 1 row. We're gonna go straight across, and the element that is right below chlorine, meaning it has 2 electrons in the S and 5 electrons in the P, is bromine. So the answer to the first practice question would be bromine. What I'd like you to do now is take a look at these 3 questions and see if you can answer these on your own. Okay, so pause the video and then come back and see if you got them right. Alright, so the first one says, which element has the same S and P as nitrogen but is in the 3rd energy level? So same S and P as nitrogen. Nitrogen is here. It's in the 2nd energy level. So we go down to the 3rd, cut back across. It's the element that's just below it, which would be phosphorus. So that answer would be P for phosphorus. Okay, next question says, which element has 2 electrons in the 4d orbital? Tricky. So 2 electrons in the 4d. Well, first of all, 4 would tell us 4th row, except it's the d block that they want. So we go down 1, right? Again, we're in the d block. So that tells us we go down 1 from the energy level that we think we're at. And then it says 2 electrons. So we go 1, 2, zirconium. Okay, so answer to the third one would be Zr for zirconium. Last question says, which element has half of its 3p orbitals filled? The tricky thing here is you got to think, okay, 3p orbitals. So in other words, p has 3 orbitals, okay? And if they're half filled, that means there's 1 electron in each, because each one can normally hold 2 electrons, right? So what this is saying is you're in the 3rd energy level with 3 electrons in the p, okay? So if we go back, so 3rd energy level, cut across to the p block, and we have 1, 2, 3 electrons filled, so we're dealing with phosphorus. All right, that's our practice. We are done. Make sure you fill out the whisk, and we'll see you tomorrow.